So, this is lecture 5 of module 1. We will continue the discussion that we did in the last class on nonlinear system analysis. So, what we did is actually in the last class we represent a general nonlinear system in a state space format. So, where this is your states and this is your output, f is a nonlinear function, it is a vector, also h is a vector, this is all n dimensional vectors, and y is p dimensional vector. So, what we said review wise, we said that how a nonlinear function can be expanded using Taylor series expansion around some point. Say this is my point, around this point I want to expand this function, then I can write as del f by del x delta x del f by del u delta u. So, this is first order expansion and some higher order term. And if x c is an equilibrium point, then f x c u e is 0. So, the linearized system around x c and u e is given by delta x dot equal to del f by del x x c u e delta x plus del f by del u delta u. So, here we in our Taylor series expansion we ignored the higher order approximation with certain condition, and we said that this is A matrix and this is your B matrix. So, this is your A matrix and this is your B matrix. So, for stability of x dot equal to f x, there are two methods we discussed: Lyapunov's indirect method and 2 is Lyapunov's direct method. This is what we discussed, and in this indirect method we linearize in indirect method we linearize x dot equal to f x as a x, where A is del f by del x. So, this is a n by n matrix, and we check if A has all eigenvalues, not all, has eigenvalues with negative real parts. Okay. If so, then system is stable. That is what we discussed in the last class. And then we discussed Lyapunov's direct method. Prescribe a Lyapunov function V x for x dot equal to f x, and then after finding Lyapunov function, we have certain properties for Lyapunov function V x that we discussed, and then we have to make sure that V dot x, if negative definite, then the system x dot equal to f x is stable around an equilibrium point. X where V x c is 0 and V x is greater than 0 if. So, this is the summary of the last class. Now, we go to the next further discussion. So, if we have linearized the system, now our actual system is x dot equal to f x, and this system, if we linearize, after linearization, we write x dot equal to x, and you say that in linearized dynamics we just make our symbols very simple. So, the linearized system is actually delta x dot equal to a delta x, but for just convenience we represent this equation as x dot equal to x of the same system, x dot equal to f x. This is our original nonlinear system, this is a linearized system, and then we concluded how to determine the stability of the linearized system. So, we discussed in the last class the direct method and indirect method. Now, can we use this Lyapunov stability theory for stability of linear system, which is x dot equal to x? The answer is yes. It seems it is very interesting to see that for x dot equal to x, there is a very scientific method to say what is exactly a Lyapunov function, and it turns out that the Lyapunov function is V x equal to x transpose p x. It is a quadratic form Lyapunov function, and this is a valid Lyapunov function. One really need not have to ache his head to find out what is a Lyapunov function for a linear system. It is very well defined, where x transpose p x and p is symmetric positive definite. That is very important. So, once we have defined V x is x transpose p x, this is our Lyapunov function, and then we differentiate V x, which is V dot x is obviously x dot transpose p x plus x transpose p x dot, and our x dot is a x. So, we replace x dot by a x. So, here a x to the transpose p x, then x transpose p and x dot is a x. So, by simplification we find x transpose a transpose p plus p a into x, which is minus x transpose q x. So, the for stability of a linear system, according to stability theory, this quantity x transpose q x should be positive definite, because if x transpose q x is positive definite, then v dot x, which is negative of positive definite, becomes negative definite. So, then what is the condition? If it is stable, then this should be positive definite. So, if x transpose q x is positive definite, the definition of a quadratic function to be positive definite is that q should be positive then. Okay. So, let me little write here that x transpose q x to be positive definite q must be positive definite. Our identity, which is a transpose p p a equal to minus q, this is our identity from here v dot x. This is known as Lyapunov matrix equation. Popularly this is also known as Lyapunov equation, and in this Lyapunov equation a transpose p plus p a equal to minus q, for stability q should be positive definite. So, we can always arbitrarily select q to be positive definite. We already know what is a and determine if p comes out to be positive definite. If that is the case, then the system is stable. So, we go by circularity. So, a transpose p plus p a is minus q. So, we select a q which is positive definite, then a is given to us. Now, we solve this equation with a specific positive definite q and then solve the equation to find p. If p is positive definite, then A is a stable matrix. That is, the system, the linear system is stable. It is not that we do, already we know that if x dot equal to x, then the system is stable if A has eigenvalues with negative real parts. All eigenvalues should have negative real part. So, that is a well known theory, we already know about it, but we say now that even Lyapunov theory, stability theory also can be used, that the direct method of Lyapunov stability can be used for linear system. So, in that sense Lyapunov's direct method is a more generalized stability theory, because using this we can determine the stability of both linear system as well as nonlinear system. This is important. The Lyapunov direct method is a more generalized stability theory and can be applied to both linear and nonlinear system. Okay. So, this we already discussed, that if the matrix Q is positive definite, then the system is asymptotically stable. Therefore, we should pick Q equal to I, the identity matrix, which is a positive definite matrix, and find if P is positive definite. If P is positive definite, then it is stable. So, the usefulness of Lyapunov matrix equation for linear system is that it can provide an initial estimate for the Lyapunov function for a nonlinear system in cases where this is done computationally. Furthermore, it can be used to show stability of the linear quadratic regulator design. Sometimes we are not very clear how to find out Lyapunov function for some nonlinear systems, and there the Lyapunov matrix equation becomes a handy. Now, this is an important theorem, Lassale theorem. It is an addendum to already existing Lyapunov stability theory using direct method. So, here if x equal to 0, origin, this is an origin, is equilibrium point of this nonlinear system, then assume that Vx is continuously differentiable, positive definite, radially unbounded, as we, and that is a property of a Lyapunov function. Then if the time derivative of the Lyapunov function V dot is less than equal to minus some function of x, where Wx is a positive definite function. Then not only Wx, here Wx is positive definite. Yes. So, Wx is a positive definite function. So, then all solution of x dot are globally uniformly bounded and satisfy Wxt tends to 0. So, we already said if B dot is negative definite, then system is stable. Now, we are only simply saying this Wx is a positive definite as well as a continuous function. Earlier we simply said it is a positive definite, now we are saying it is a positive definite as well as continuous function. When these two are together true, then what happens? This is also true. Wxt will at t tends to infinity will become 0, and this is Lassala-Losija theorem, and this theorem is very important to determine the convergence of trajectories, as we will see later in this course. So, this is what, if Wx is positive definite, then the equilibrium point is globally uniformly asymptotically stable. So, now we will discuss more examples using these concepts. So, what we discussed now, Lyapunov direct method, indirect method, and how to apply Lyapunov's direct method to linear system, plus Lassale-Losija theorem that gives the convergence property of the function that Wx, which is it goes to 0 as t tends to infinity. Now, we will talk about now Lyapunov's examples for Lyapunov's direct method. So, these three questions we will try to answer. How to assess the importance of nonlinear terms in stability or instability? How to estimate the domain of attraction of an equilibrium point? How to design a controller that guarantees global asymptotic stability? So, these three things. So, we will take one example here. In this example, we will show that how using Lyapunov's direct method we can find out the domain of attraction. So, x 1 dot is minus x 2 a x 1 x 2 square, x 2 dot is x 1 minus b x 1 square x 2, where a is not equal to b. This is important condition. So, first of all, we through this example we will compare direct versus indirect. That is, we linearize the system, look at the stability, linearize the system, and then as a whole we apply the direct method and look at the stability, and we will see what is the difference. So, let x 1 bar and x 2 bar. So, this x 1 bar and x 2 bar are states corresponding to equilibrium point. So, if you put x 1 bar x 2 bar here, then at equilibrium point the dynamics becomes standstill, there is no dynamics, meaning this becomes 0, this becomes 0 at equilibrium point. This is very important. At equilibrium point, what is equilibrium point? At a point where there is no more dynamics. So, x 1 dot x 2 dot they all become 0. So, if you put this, then we find what are the equilibrium points. So, obviously, you will see that equilibrium points, the solution, because a minus b is not 0. So, this, because since this quantity is not equal to 0, obviously, x 1 square and x 2 square has to be 0. And so, if you go back to the previous one, if you consider in this x 2 equal to 0, if this is 0, then x 1 has to be 0. Similarly, if x 1 is 0, then this quantity becomes 0. So, x 2 has to be 0. So, finally, the net result is the origin is a equilibrium point, x 1 equal to x 2 equal to 0 is the equilibrium point. So, we linearize using the linearized concept. So, this is our result, x 1 dot x 2 dot. How did you find this 0 minus 1? Please verify, this is actually del f 1 by del x 1, del f 1 by del x 2, del f 1 del f 2 by del x 1, del f 2 by del x 2 at x 1 equal to 0, x 2 equal to 0. Okay. So, what is f 1 in this case? So, x 1 is x 1 minus x 2 plus a x 1 x 2 square x 2 dot is x 1 minus b x 1 square x 2. So, this is our system. So, this is my f 1 and this is my f 2. So, you differentiate this f 1 with respect to x 1, which is 2 a x 2 square a, and if you put x 2 equal to 0, this becomes 0. And similarly, del f 1 by del x 2 is actually minus 1. So, this is minus 1 at any value. So, this is minus 1. Similarly, if you differentiate f 2 with respect to x 1, first element is 1, second element is 2 x 1 x 2 into minus b, and by putting x 1 equal to 0, x 2 equal to 0, this second term becomes 0. So, 1 is retained, and you can verify also del f 2 by del x 2, which is minus b x 1 square at x 1 equal to 0 becomes 0. Hope that is very clear to you how to linearize a nonlinear system around an equilibrium point. So, this is should be very clear to you. So, what we found out? We found out that x dot equal to a x, the linearization around x equal to 0 is x dot equal to x, where a is 0 0 minus 1 plus 1. This is the matrix we obtain, and this you can easily check that the eigenvalues of A are s square plus 1 equal to 0. So, s 1 s 2 are plus or minus j omega. So, the eigenvalues are do not have negative real part. So, by using Lyapunov indirect method, we cannot determine the stability. So, indirect method fails to determine the stability, since it does not say, because for saying stability or instability, either the real part has to be, all real part has to be either negative or all real part has to be positive. If it is negative, then stable, all negative, all positive, unstable. But what happens when the eigenvalues are 0, or like here in this case we found out plus or minus j omega, 0 real part. So, in this case indirect method fails, is silent, it does not say anything about the stability. But let us go to the for this system, indirect method fails. Now, go to direct method. We apply direct method, and in a direct method we assume the Lyapunov function, which is a quadratic Lyapunov function. We have two states x 1 and x 2. So, simple is half x 1 square plus half x 2 square, and we differentiate v dot x, okay, and this, as you know, that this is our f 1 and this is our f 2, and you replace, because if I see here v dot, here v dot is x 1 dot plus x 2 dot. So, that is what I am doing. X 1 is here and this is my x 1 dot, this is x 2 and this is my x 2 dot. And if I finally simplify it, I get a very nice expression here, and this expression is a minus b x 1 square x 2 square. So, you can easily see that this is negative if minus delta square, where delta is b minus a and positive. Okay. So, that is if A is greater than A is less than B, if A is less than B, then this becomes a negative definite quantity and hence the system is stable. So, the answer is very simple. If A is greater than B, system is unstable. If B is greater than A, system is stable using direct method. So, that is an interesting application. So, we see that if A is less than B, the system is asymptotically stable, but if A is greater than B, the system is unstable. So, this result cannot be obtained by linearization using indirect method. Now, we go to the another example. So, this first example what we did is that what is the advantage of a direct method over indirect method. That is simple, because in some cases indirect method is silent about the concept of stability, but in direct method gives that. Now, we take another example where x 1 dot is this, x 2 dot is this. You can verify, this is an exercise for you, verify that so verify this x 1 equal to 0 and x 2 equal to 0. You can easily see that, because if this is 0 all zeros, then this becomes also 0. So, obviously, this is an equilibrium point. Now, the question is, what is the stability about this equilibrium point? How stable this equilibrium point is? That is the question. You linearize, again we go back to the indirect method, linearize the system, verify that the linearized system of the original x dot equal to f x is minus 1 1 minus 1 minus 1 x 1 x 2. So, in this you can see the characteristic polynomial of this concerning this A matrix is s square plus 2 s plus 2 equal to 0, and you can easily see that this particular system has all eigenvalues, that is negative, because s 1 and s 2 is minus 1 plus or minus j 1. So, obviously, the system is stable. So, indirect method also provides or gives us the solution that the system is stable around the equilibrium point, but it cannot say that how this equilibrium, how much stable is this equilibrium point. There is no quantification about it, that if I disturb the system from the equilibrium point, that is origin, to a very, how much I can disturb from this equilibrium point, and still I can say the system is stable. So, that answer will not get using indirect method. So, that is called, if the initial condition is close to the equilibrium point 0 0, then we can say the system is stable using the concept of Lyapunov's indirect method. But now, let us go to the direct method. The indirect method cannot say what is the domain of attraction, that is, this is my x 1, this is my x 2, this is my origin. So, the indirect method said, if I disturb this origin to this point, then I can come back to here. But how far I can disturb this particular origin? Can I disturb to this point further, and where I will fail? So, let us go to the direct method to answer this question, which is called domain of attraction or region of attraction. So, V x is half x 1 square plus half x 2 square, apply the derivative x 1 dot x 2 dot, and I think there is some mistake here. So, this is our f 1 and this is our f 2. So, if we simplify this v dot x, then we get an expression like this: x 1 square plus x 2 square is x 1 square plus x 2 square minus 1. So, this gives me, this will become negative definite or this v dot x is negative definite if x 1 square plus x 2 square is less than 1. That means, this quantity is negative. This quantity you can always say this is positive. So, this will become negative definite, this is always positive. So, this will become negative definite if this becomes a negative, this becomes a negative if x 1 square plus x 2 square is less than 1, and that is the condition for which the system is stable. So, obviously, this gives me region of attraction, because this is my x 1, this is my x 2, this is my origin. So, obviously, this is a circle of radius 1, this r equal to 1. So, if I am my initial system initial states are anywhere inside this region, this is always positive, and if this can be made negative, then the system b dot x is negative definite. Using Lyapunov direct method, we conclude the system is globally stable, but then the region of stability is, it is not globally stable, this is asymptotically stable, and that stability is guaranteed as long as your initial the system initial state are disturbed, and the disturbed initial states, they lie inside this circle, and circle has a radius 1, x 1 square plus x 2 square equal to 1. So, this means that the domain of attraction of the equilibrium point is a circular disc of radius 1. As long as the initial conditions are inside the disc, it is guaranteed that the solution will end up at the stable equilibrium, that is origin 0 0. In case the initial condition lie outside the disc, then convergence is not guaranteed. It should be mentioned that the above disc is an estimate of domain of attraction based on the particular Lyapunov function we selected. A different Lyapunov function could have produced a different estimate of domain of attraction. Okay. So, if another Lyapunov function may even determine a domain of attraction for where the domain of attraction that we found will be a subset, or it may find a domain of attraction which will be a subset of our the domain of attraction that we have just found out. Now, we will we just gave certain ideas about how to determine the stability using Lyapunov stability theory, both indirect and direct method. Now, we will go a little further in terms of application to control system design. So, we will just take some example in this class. So, this is a trajectory tracking example. What you are seeing is that this is a dynamics of a single link robot manipulator. You see, this is a one link, there is a one link, a rigid link, this is a rigid link, and this rigid link is mounted on a motor. This rigid link is mounted on a motor, and this moves in a vertical plane. Means this is like, there is a motor, and so this is my motor here, and this is my rigid link, and this rigid link moves in the vertical plane. Motor rotates this rigid link in the vertical plane, okay, and there is some friction here. The motor shaft on which the link is mounted, there is some friction. So, the equation is ml square theta double dot plus k theta dot plus mgl cos theta equal to tau. So, theta is this angle. So, the objective is to find a control law, so that theta tracks a desired trajectory theta d. So, I'm moving my hand like this, this is my, and this should follow any trajectory that I want it to follow, whether it is a sinusoid trajectory, a set point. This is a sinusoid trajectory with constant amplitude and maximum amplitude, from one point to another point it goes, and you can go also set point tracking, any trajectory. So, now we define trajectory tracking means, so this is my theta d, theta d can be set point, theta d also can be a sinusoid trajectory, it can be also exponential trajectory, this is theta d. So, this is initial theta and final theta is here and it follows there. So, objective is how what should be my control law, that how much torque this motor should develop and apply to this link, such that the link follows this desired theta angle, desired angle. The position of the link is given in terms of the angular position is always following given theta d, desired angular position. So, for that what we do, we define E equal to theta minus theta d. So, the error gives us an idea how close my actual theta, the angle of my link, from the actual trajectory. So, by putting E equal to this, we can show that the error dynamic equation is ml square E double dot plus k E dot plus mgl cos theta equal to tau. So, this is an example that will show an application to controller design using Lyapunov stability theory. So, we talked about in this we will take a single link manipulator. A single link manipulator means you have one rigid link here, and this rigid link is mounted on a motor shaft in such a way that this rigid link moves in vertical plane, not horizontal plane, not this, it is in vertical plane. Okay. And assuming there is some friction at the shaft where the motor is the link is moving. So, we can write the dynamic equation as ml square theta double dot plus k theta dot mgl cos theta equal to tau. If you have a little difficulty with this dynamical equation, kindly refer any book on robot manipulator, you will understand the dynamics of a robot manipulator from a book. Now, we are not interested how we got the dynamics, we are interested if given a dynamics how to control the robot manipulator, a single link manipulator. So, this is my dynamics, this is my applied torque tau, tau is applied by the motor here at this point, this is my single link, motor is applying a torque here, and this torque is making this move, this link move in vertically at some angular position theta. Objective is theta should follow a particular trajectory theta d, but here theta d is a constant reference. So, although this we are say trajectory tracking, this is actually a set point tracking. So, this is my dynamics, and I want that whatever my initial angular position of this link, it has to go to a desired theta d, whatever my actual angular position. So, how do I actuate a torque here by the motor such that this link goes to any point, any angle. So, we define an error theta minus theta d, how far it is from the reference point, and then you can easily say that theta double dot d is 0 and theta dot d is 0. This because theta d is a constant reference. So, theta double dot d is 0 and theta dot is 0. So, using these two ideas, and we can always add theta double dot minus theta double dot d. Similarly, here theta dot minus theta double dot d. So, I subtract here theta double dot d and I subtract here theta dot d, because this is 0, this is 0. So, my dynamics remains unchanged, but this gives me an error dynamics where ml square E double dot plus k E dot equal to mgl cos theta plus mgl cos theta equal to tau. Now, for this error dynamics, I define a Lyapunov function, which is half ml square E dot square plus half k p E square. As I said you in last class, that these Lyapunov functions we have proposed based on some experience. It is not exactly a science, it is just an art. Based on our experience, we have to make sure that we have proposed a Lyapunov function which is positive definite. So many ways, but for this we designed this, and time derivative of V dot is ml square E dot E double dot plus k p E E dot. So, this is not u, this is actually tau. So, you see that we found out in the just now E double dot plus k E dot plus mg L cos theta equal to tau. So, from here we can write E dot to be minus k E dot minus mgl cos theta plus tau and 1 by ml square. So, this ml square is multiplied with this ml square, that becomes 1. So, we have here tau minus k E dot minus mgl cos theta, and then this particular here also, this is k p E E dot. So, now I can take this E dot also as a common, then k p E will come inside. So, E dot, if I take common, this is tau minus k E dot, this is the torque developed by the motor, minus mg L cos theta plus k p E. So, this is the V dot. So, obviously, to make it negative definite, I must make this quantity I should adjust this quantity in such a way that this becomes negative definite. Can you think that how this can be made negative definite? You see that this can be made negative definite if tau is mgl cos theta minus k p E. You can see that, because in that case this term will be minus k E dot, and you have so many ways to propose what should be my controller law. You see that how we are using Lyapunov function or Lyapunov stability theory to design controller. We do not know what is tau, we have to design tau. We are given a dynamics, we proposed a Lyapunov function, we found out the time derivative of Lyapunov function, and we reached here. Now, here is an option for you, how do you select tau in such a way V dot is negative definite, such that the system is stable for that controller, the controller that you proposed. So, here, so obviously, if I simply make u equal to mgl cos theta minus k p E, Then in the previous this thing slide we saw that simply it can be equal to E dot minus k E dot square, but that does not guarantee me asymptotic stability. You will see that, and that is the reason why we added another term called minus k d E dot. By doing that, V dot becomes minus k d plus k E dot square. Hope you are very clear about this. And obviously, why? Because initial k may be positive and negative. Now, k d plus k, because k d is my extra parameter I provided, even k may be a very small quantity. So, the k d E dot was actually introduced to make this quantity reasonably large, and now this is a positive quantity, E dot square is a positive quantity. So, V dot becomes negative definite. So, this implies that, and you see that Lassale-Ashijara theorem says when V dot becomes a function like this, and this is a continuous function because E dot is a continuous function and this is a negative definite function, and then sorry, this particular quantity is a positive definite and this will converge to 0, because E dot square converges to 0, E dot also converges to 0, because E dot converges to 0, E double dot converges to 0, but does not guarantee, this does not imply that E goes to 0. If E dot goes to 0, E double dot goes to 0, but does not imply that E goes to 0. So, we take this control input and replace this control input in our, so this is u or tau. Normally we the control input is denoted by u, but actually this is tau, and our actual system is theta double dot ml square plus k theta dot plus mgl cos theta equal to tau. So, this tau is here and I bring this quantity and put it here. If you put it there, you get this equation, and this is complete error dynamics. This is actual error dynamics given the control law. So, once this error dynamics is known, from here you can see, because E double dot is 0 converges, E dot goes to 0, obviously E has to go to 0. So, this implies E is 0, E dot is 0, E double dot is 0, that means the my link, whatever may be the initial position, it will exactly go to the desired position. I hope you could appreciate this particular example. So, this what you saw is that an example how we can actually use Lyapunov stability theory to design even a controller, and we use Lyapunov stability theory and Lassale-Ashijara theorem to show that how finally the single link manipulator will follow a given set point exactly with no steady state error, right. So, this is very important, because in this course we will use most of the time this Lyapunov stability theory to show that our system is stable, trajectory convergence is there in any control. Most important is that in control system design, of course nonlinear. When we say intelligent control will always apply to nonlinear system. So, first is stability, and then trajectory tracking, and in this case we showed using Lyapunov stability theory E goes to 0, E dot goes to 0, E double dot goes to 0, where E is theta minus theta d. That means, theta follows theta d. So, that is the objective of intelligent control. Okay. How accurately, but we have not done here, this is classical control system. We will talk also in this, these are the basics we must have. So, in the next class we will discuss that how we can use this Lyapunov stability theory. We will use Lyapunov stability theory to train neural networks. Okay. So, why we are learning this? Because these neural networks are good tools to perform system identification. Nonlinear system. So, next class we will, that is the reason I introduced now what is Lyapunov stability theory, and we will use this concept to train the neural networks in the next class. And for your further reference, here is the same books that I said also in the last lecture. These are the books that you can follow for grasping the concepts or the ideas that we discussed now. Thank you again.